Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Mike Borza of Synopsys. We're going to talk today about die-to-die security. Mike, as we start putting multiple die or chiplets into a package, we're starting to deal with security issues we never had before because in some cases, these are multi-vendor. In some cases, they're connected in ways that they never were before. Where are you seeing the problems today?
Thanks, Ed. I guess the problems really are a kind of a hybrid between the kinds of things that you see at board level. So really, you can think of multiple die in a single package as a kind of compressed board level design. And so you have some of those same issues. You want to ensure that the chips around the system are the correct ones, that you're talking to the right things. And people didn't used to worry about that too much because they had good control of their supply chains and their suppliers and all of the things that they were going to put down. So they didn't need to go to a lot of trouble to authenticate those things. But as you get into these kinds of systems where you've got multiple suppliers participating in an ecosystem, you may be getting some standardized functions that meet a particular chiplet spec. And so those things, you need to authenticate them as you put the system together. Make sure that the system that you have is the system you thought you were building. And so that's the first thing. So identification and authentication of the parts is a huge part of this. There are different ideas for how to do that. You may use endpoint authentication between die, but it's also, there are people that are thinking that they can use a kind of an intelligent interposer or an interposer with some extra functions or a supervisory chip to start stitching the system together at that level. So compare that to an SoC. It's much more certain with a large SoC that all of the parts that are separated out to become chiplets in a system and package kind of configuration, those things are all part of the same die. And so you don't have that same level of concern about the authenticity of the component parts of the system in a system on chip implementation.
Well, you also have chiplets is because you can't fit everything on a single die anymore. There's a lot more data to process, and that data is becoming more valuable too, right? So now instead of just going after all the data and saying we can get into this chip and control it, we now can slice off pieces of this, and that's valuable too. How do you deal with that?
Yeah, that's a great point. There are really two things. We're approaching the limits on the size of the die. Well, we've been at those limits for a long time now. Really, sort of the extent of it, what you want to do is 14 or 15 millimeters on a die side. And so with each shrink of technology, which we're running out of in the future, but we've got a few more steps to go. You're going to be constrained to how much functionality you can fit into one place, not to mention how much power you can shed from that single die. And so breaking up large functions or standardized functions into chiplets makes a lot more sense. And so at that point, you've got now this notion that you need to have the ability to establish some authenticity. I'd say some of the biggest users of this technology are the people who operate large data centers. So the Googles, the Amazons, people like that, the pure play data center providers, and all the people developing server class chips of different persuasions, whether those are GPU servers or AI servers to plug into a rack or those kinds of things. And so you end up needing to build up a system of all these components that have very different functional purposes within the system. Interesting in all this is that you have these multi-tenancy situations, and especially in data centers, this is a concern, where people who don't know each other, or maybe some people do know who they're sharing a rack or a system with, are trying to use that opportunity to find out what's going on in the adjacent compute infrastructure to what they're in. And if that's a virtualized infrastructure, that gets to be a real concern, because now you have opportunities for side channel attacks. The vendors of the processors are all trying to minimize that opportunity, but you have these kinds of concerns that you have multiple people in the same place. And so being able to establish who's using the infrastructure and what parts of the infrastructure are they using. If you have a shared FPGA or a shared GPU, and that GPU is processing a learning workload for a ML system, then you've really got concerns about who else you're sharing that rack with, because you don't want them to be able to possibly intuit what you're doing.
We're seeing sort of a succession of breaking into chips and breaking into systems that were considered secure in the past. It started out with perimeter security, which was considered the way to keep everybody out, and that failed. Even when we got to virtualization with hypervisors on there, everybody thought those were going to be secure. They can be attacked as well. FPGAs can be attacked. Now we've got all these elements in one package. Does that make it more vulnerable?
It creates a much larger security attack surface. And so, the number of things that need to be secure and remain secure in order to maintain the overall security of the system just increases. And, we've seen adversaries that or attackers who take advantage of the fact that a weakness in one spot becomes their foothold in the system, and they can sit and snoop for a while. They can use it as an opportunity to escalate their attack somewhere else in the system. Oftentimes, peripherals in systems, things we used to think of peripherals, it's not that long ago we thought of as GPU as a peripheral, not a main compute element. And those subsystems didn't have any notion of real access control or of multi-tenancy or anything else. The idea that you could share information through those things, or that someone could use that as an opportunity to listen in on what somebody else is doing, never really occurred to people. And so that has changed a lot in the last few years. But I would say the other thing that changed is that it was not really the case when virtualization started, at least in the current data center context, that people assumed that they'd be sharing a single physical CPU with multiple other users from different places who they don't know, and just leasing space on that CPU. So virtualization started out as a way to isolate applications from each other and as a way to isolate workloads from each other, but not necessarily with the notion that some of those workloads would be adversarial. And now that, is an assumption that fails. And of course, we've seen several years of attacks in which those have failed spectacularly.
Where we're dealing with different aging of these chiplets or within a package. And these devices may be in the market for longer than they were in the past. You think about automotive, for example, they're looking at chiplets as well, but in automotive, these things are sometimes in the market for 10 or 15 years. What sort of problems does that bring in, and how do you address that? Is it just something that you need to constantly have access to and say, okay, we can adjust whatever security we have as we go, or is it something you put in place to begin with?
Well, you generally try to put in place a high enough level of security at the outset that, for your intended operational model, you're providing adequate protection for people. But it's with the knowledge that security is degrading over time. And so it's going to require constant care and feeding to keep that system secure, if that's to be done. And this has always been true with long life systems. The running joke about automotive is that it's mil spec at consumer prices. And, I think that has started to change, that people are starting to understand that, a huge amount of the value of the vehicle is in the electronic systems and the value add that they bring. And so those are starting to be recognized for what they are. And they're also providing, the automotive manufacturers opportunities to innovate that they haven't had in the past. They can innovate more quickly in their vehicle designs, and they have the flexibility to be able to upgrade things through firmware and software that they weren't able to do before. And so it keeps their current generations of products alive for longer. So I think you're starting to get those kinds of benefits from this scenario. And in order to make that all work, it's going to take real security to, again, put these systems together. And, you know, the whole notion of putting, say, a system in package together in which you authenticate all of the parts, all of the chiplets or dilets in the package to each other. All of the ECUs need to authenticate to each other as well as you build the network in the car up. And so you're really building layers of networks in these kinds of systems.
So instead of just security as a thing that you put into a system, it's now almost a stack, right? And that stack now has to exist in 4 dimensions because it changes over time.
Yeah, exactly right. And really, you know, one of the things you mentioned just a minute ago was the notion that you've got parts of the system in package that may age at different rates because they're different technologies fundamentally, or they have different technology, even if they're all silicon. But you know, it's not uncommon to find gallium nitride or some other semiconductor in a particular application because it's the best material for the job. And what that does create is some opportunities to use on system instrumentation to assess what the aging of the relative components are, what the relative aging of the components are. And this gives you ways to start understanding things about your system that prove to you what's an authentic system, what's not an authentic system, how the average system behaves over time and as the system ages, and the possibility of detecting when, you know, a population of these chips or of these systems is actually under threat because it's being attacked actively, and you can start to see different behaviors in those systems. So the measurements that you can make using these different components, or the components that are you know, fundamentally different, that we can do differential aging analysis or differential comparisons on, gets to be a way to use it as a monitor of unwanted activity.
As we get into denser designs, does it become harder to safeguard them against attacks? You've got thermal movement inside of those designs. You can tell when something's happening, right?
Yeah, that's true. So that kind of goes back to what I was saying about it creates the opportunity to measure when, use thermal properties to measure when something is happening in the system that you weren't expecting. And you know, some people are using those thermal sensors, and especially the on-chip thermal sensors, to sort of balance workloads across parts of the chip. But in cases where you have something that has an expected behavior and expected activity level, if that's running hotter or colder than you expect it to, that tells you a lot about you know, what is going on in the system. You can use that to infer things about what the activities are. So that thermal you know, management task gives you both opportunities to manage, you know, how hard things are working within the chip, and potentially, you know, manage things like we're going to drive this part of this chip into failure or early death because it's running so hot. Can we balance that out by moving the work somewhere else? And it also gives you this opportunity to treat that as a sensor that's an indicator of potential misbehavior of the component.
In theory, you want data encrypted as it comes into the chip, but does it stay encrypted as it moves from chiplet to chiplet within the chip or within the package?
It typically doesn't, because right now it's inefficient to try to operate on encrypted data. But as you move data from point to point, you want to be able to secure it. And so for some cases, it makes sense to use what's essentially inline encryption and authentication to verify the integrity of the data and to protect its confidentiality. And so that's going to be a part of the solution for parts of the system. In some cases, it's unnecessary to do that. For example, if you consider moving data in and out of memory, you don't need to, the memory doesn't need to encrypt or decrypt the data. It can store it encrypted. But when you bring it back in, it's going to be decrypted. And that creates a need for things like inline memory encryption engines that are capable of encrypting and decrypting data as we bring it in and out.
So, Mike, we've got a whole bunch of issues here that we have to deal with, and they're just going to probably grow over time because this just becomes more complicated, and security is always an ongoing challenge. You've got authentication issues, you've got die-to-die data communication issues, you've got upgradability over time. What's the outlook for all this? Are we going to get to the point where we really have to put into some sort of format, almost like what we do for design for power, design for throughput, design for context? Do we now need design for security?
Well, I think that that's exactly right, Ed. If you look at the kinds of work we did in the DARPA ACE program, it was about automating the inclusion of security in the overall SoC design. I think that we're going to see that kind of thinking brought to bear on the 3DIC and the 3DHI kinds of worlds. So you'll see more systematic thinking about security, systematic ways of doing the same thing that, basically make it easier for people to get it right. That's what you want to do, is not require everybody to have a security expert everywhere all the time, but to have, good systematic solutions that can be deployed and used reliably, and that are designed from the outset to be upgradable to adapt to the threat as it changes over time. So that's a huge part of this. I think if you look more broadly at what's happening in, say, computer system architecture today, and especially in the data center, that's indicative of what is going on here. And, you start to see things like IDE on PCIe. Nobody would have thought that we're doing, 64 giga transactions per second, and they're all encrypted and authenticated. And yet we are. And so that's starting to be part of the thinking about how you build these systems and make them secure, make them robust, and stand up to the kinds of things that we're seeing as threats. And so I think it's inevitable that 3DHI is going to go in the same direction, and that we're going to be looking to try to have good systematic solutions that can be deployed fairly easily by people who are not necessarily experts at security, but they're experts at putting their systems together, and they're very good at following a template and a roadmap that helps them to get that right.
So it used to be it takes a village. Now it's going to take a bunch of villages to get this done.
A bunch of villages. I guess it will. It's a learning process, and we've talked about this a number of times over the years. And, at various times I've been skeptical that people were going to get the message that when they're building an SoC, they needed to have even one root of trust in that SoC to at least get the system up and running the first time at cold boots securely. And now that's becoming commonplace. And we're starting to see that, people are starting to understand the importance of security and how it is a first-class design parameter of the system. And so it's not just power, performance, and area, but, PPA plus security.
Mike Borza, as always, thanks for a great explanation.
Thank you, Ed. My pleasure.